Hi everybody, thanks for watching this video. I'm Giulia Rambelli, and in what follows I'm going to talk about logical metonymy and how computational models can assign the correct interpretation to a metonymic sentence. In this video I will explain the resources and the models we selected for the task, and I will discuss the obtained results. But first of all, what is logical metonymy? Here there is an example of a metonymic sentence. The pianist begins the symphony. The peculiarity of this sentence is that the event the sentence refers to is not lexically expressed. In other words, it is not explicit what the pianist started to do. However, the majority of English speakers could say that the correct interpretation of the sentence is actually the pianist begins playing the symphony. Formally, the phenomenon of logical metonymy is defined as a type clash between an event-selecting metonymic verb, begin, and an entity denoting nominal object, symphony, which triggers the recovery of an hidden event, play. Still, the cover event is also conditioned to the subject of the sentence. In "The composer begins the symphony," the metonymic verb and the object are the same, but the different subject involves the retrieval of a different verb, which is write. Therefore, the interpretation of a logical metonymy depends on the mutual typicality of both the subject and the object. Logical metonymies have been widely studied in both linguistics and cognitive science. In theoretical linguistics, they represent a challenge to traditional theories of compositionality, as it arises the problem that the conceptual structure of the sentence contains material not expressed at the lexical level. On the other side, they received extensive attention in cognitive research on human sentence processing. In particular, psycholinguistic work has demonstrated extra processing costs for metonymic constructions. The recent hypothesis on logical metonymy interpretation is that speakers quickly make use of their rich knowledge about events and their participants to build expectation about their upcoming input. That means people use contextual cues to retrieve the hidden event. In this scenario, our research question is: are computational models able to exploit contextual cues in order to correctly retrieve the cover event, and which are their limitations? Given this premise, I can start to explain the details of our experiment. We define the task of logical metonymy interpretation as a cover event recovery task, or, in other words, retrieve the most likely hidden verb for a given sentence. Starting from a metonymic triple, a computational model quantifies the typicality of a verb associated to the target triple using a plausibility score. All models are evaluated on their capability of assigning a higher plausibility score to the verb that refers to the correct interpretation. To perform our experiment, we use 3 datasets designed for previous psycholinguistic studies: the McCurry dataset, the Tralaxer dataset, and the Lapata and Lascarides dataset. And we also use a new dataset created by the authors that we call Recovered Cover Events Dataset, or CE. For the first 2 datasets, the models have to perform a binary classification task. Each triple is associated with 2 verbs, a typical and a less typical one, and the model is evaluating on its capability of assigning a higher probability to the verb representing the typical condition. In the case of the latter 2 datasets, for each model we compute Spearman's correlation between the probabilities generated by the models and the scores resulting from human judgments. The higher is the correlation, the better is performing the model. We test different computational models for logical metonymy interpretation. The first one is the probabilistic model, previously introduced by Lapata and Lascarides and re-implemented by Zarcone in 2012. The probability baseline models the interpretation of a logical metonymy as the joint distribution of the subject, the object, and the hidden verb. As for the distributional models, they make use of static word embeddings, and they define the recovering of the cover event as identifying the verb with the highest thematic fit with a metonymic sentence. While the thematic fit model makes use of simple statistics extracted from Wikipedia corpus, the structured distributional model represents sentence meaning with a combination of formal structures and distributional embeddings. Last but not least, we experiment with 4 transformers models, which have been shown to obtain state-of-the-art performances on several natural language processing benchmarks. For BERT, Roberta, and ExcelNet, we perform a word prediction task. We turn the test triples into full sentences, and we mask the verb with a special token. We then compute the probability of a hidden verb to occur in that position, and we expect that the preferred verb to get a higher value. As GPT-2 works as a traditional language model, we adopted this model to calculate the probability of the entire sentence. In this case, we expect that the sentences evoking more typical event get higher values. To the best of our knowledge, we are the first one to include the recent transformer-based language models into a contrastive study on logical metonymy. In what follows, I will present in detail the results of the models over the 4 datasets, distinguishing between the binary classification task and the correlation task. As concerning the binary classification task, this table reports the accuracies obtained by all models. Regarding the probabilistic model, the scores are very similar to the one of the thematic fit model. However, the main issue of probabilistic model is its coverage. In fact, this model covers only a subset of all items, 60% more or less, so we cannot really compare it with the other models. Looking for the best performances, GPT-2 achieves the best score for the Macquarie dataset, 0.87%. However, a statistical test demonstrates that the improvement over Roberta and SDM are not statistically significant. For the Tralaxer dataset, both Roberta and SDM achieves the same score, even if GPT-2 performs similarly. To comprehend in which cases these models are not performing correctly, we plotted a heat map visualizing the correctly predicted tuples in blue and the wrong ones in yellow. The first observation is that some pairs are never predicted correctly, and these cases are corresponding to the full vertical yellow lines in the 2 heat maps. These pairs correspond to the sentences I reported here, and they correspond to cases in which a model must discriminate between the verb read in the high typical condition and write. The fact that no model can correctly classify these cases tells us that their interpretation is not trivial, requiring high typicality knowledge. Another observation is that 2 cases are correctly classified only by SDM, that are the stylist starts the braid and the auditor begins taxes. So you can see there is only a blue piece here and the rest is a full vertical yellow line. It is possible to affirm, given this result, that all models regularly tend to prefer a verb with a more generic and undetermined meaning, that are make and do respectively, while only SDM correctly assigns the atypical class to the verb that indicate more precisely the manner of the action, braid and audit respectively. Let's now discuss the correlation scores. The probabilistic model has still coverage issues, but it reaches 86% of coverage for the Lapatin-Lascarides dataset. Still, TF model does not outperform the probabilistic baseline. As you can see, the scores are very low. And for the best performances, Roberta achieves the best score for the Lapat and Lascarides dataset, reaching a statistical significance of the improvement over SDM, while for the other dataset the two models perform in a similar way. Generally speaking, all these scores are lower than the previous task, and this could be caused by the fact that the task is intrinsically more complex, but it could also be influenced by the bigger size of these two datasets. Concerning the error analysis, we select the best model for the two datasets, and we plot the linear relationship between the human ratings on the x-axis and the model-derived probabilities on the y-axis. As you can see, SDM performance produces a large amount of variance, and there are quite a few outliers. While for the results of Roberta against the Lapat and Lascarides dataset, the majority of points follow a roughly linear relationship, and there is a small variation around the trend. To conclude, I would like to summarize the results of this experiment. First of all, even if the probabilistic model shows a good performance, it is not comparable with other models, as the majority of data points are not covered by this approach. Other models, on the contrary, do not present this issue. Another observation is that the thematic fit model never significantly outperforms the probabilistic baseline. So we can affirm that this distributional model is not powerful enough to infer logical metonymies. Among all transformer-based models, XLNet is the one performing the worst. As you can see in the previous tables, in all cases its score is lower than the probabilistic baseline. Transformer-based models tend to have a wavering behavior, which results in large differences between the dataset score. For example, GPT-2 reaches the highest performance for the Macquarie dataset, but it obtains lower scores for the other datasets. As the error analysis also revealed, transformer models struggle in perceiving different nuances of typicality. So they have a hard time in identifying the correct verb when the typicality difference is more subtle. Last but not least, the main outcome of this work is the performance of SDM. It achieves the best score for the Tralaxer and the CE datasets, obtaining the same performances of transformer-based models like Roberta, even if it's trained on a smaller corpus and without any advanced deep learning techniques. To conclude, the experiment I introduced in the slides shows how the logical metonymy task is a testing ground to check whether computational models encode common sense event knowledge, and which are still their main limitations. Thanks all for watching this video, and if you have any question, please join at the online conference on December the 5th.